Hello, everyone. This is Qing Hu, a master student majoring in nuclear engineering. The title of my thesis is Triangularity Effect on the ExB Shearing Rate in Tokamak plasmas. I will introduce the negative triangularity plasma and show my motivation. I will go through the method I used in this work, and I will analyze the effect of triangularity on the flow shear. I will discuss about the flow shear in negative triangularity plasmas, and I will show a summary and my future plan. Here, this figure shows the cross-section of the conventional positive triangularity plasma. And the red figure shows the mirrored one, that's the negative triangularity plasma. And it has many merits. TCV Tokamak has reported enhanced electron heat confinement, and recent D3D experiments has shown high beta and high confinement time operations. And other merits include no confinement degradation, reduced fluctuation, and high LG transition power threshold. That means the plasma could operate without ELMs, avoiding many difficulties from ELMs. So given that confinement has been improved and LH transition power threshold has been increased, our motivation is that how is the ExB shearing rate impacted by negative triangularity? So we start from the Hamburg formula, which is for the ExB shearing rate in generally shaped tokamak plasma. We use the conventional treatment, and we finally get the widely used formula for the shearing rate. Then we employ the Miller's equilibrium model. So for now, we can focus on this factor, which is named form factor. We can transform it in Miller's geometry into this form. And it determined the toroidal variation of the flow shear. If we consider high aspect ratio tokamak configuration, the capital R doesn't vary so much along the flux surface. So we can, for now, just focus on the factor delta R. It is written like this. In this slide, I use cartoons to help understand how the delta R is impacted by triangularity. And if you think about it, the small delta R times the inverse of delta R to measure the distance between points on two flux surfaces, like this distance and this distance. For this case, it's a positive triangularity. So we can see that this space is narrower at this point. So delta R peaks at this point. So in this low field side, we say delta R bifurcates. Inversely, for the negative triangularity case, the delta R peaks at the low field side midplane. This effect could also be understood in terms of flux squeezing. For mathematical demonstration, I just remained the effect of triangularity and its increment. So in this figure, we can tell clearly that the delta R bifurcates in the low field side This is a positive triangularity case. And for the NT case, we can see a peak at the low field side midplane. So PT and NT impacts the distance variation between flux surfaces differently. So they impact the ploidal peaking of flow shear differently. In this slide, I calculate the normalized form factor with the parameters from these 3D plasma experiments. In those figures, this axis is the ploidal coordinate theta, and this axis is the normalized psi. So for the PT case, we can see a bifurcation in low field side. And for the NT case, we can see a strong peak around, at the low field side midplane. So, yes, we found that we got different results with others, and after carefully distinguishing the effect of shaping factors, we found that in our case of calculation, the effect of delta prime dominates, delta prime dominates the ploidal variation of the form factor. That's the reason. And we plotted the radial variation of flow shearing rate. If we compare the NT case and the PT case, we can find that in the core region, the NT case shows higher flow shearing rate, but in the H region, the PT case shows stronger flow shear. We can regard it as a possible reason that possible factor that has a positive contribution to the enhanced confinement, because in this region, the NT plasma has higher flow shearing rate. Then we transformed the Hamburg formula into this form. In this form, we can clearly tell the magnetic shear dependence of the flow shear. It enters in this term. Then we plotted, we plot the flow shearing profile, shearing rate profile in part. So the solid line denotes the profile from BDT theory, and the dashed line is the magnetic shear contribution term. If we compare the PT case and the NT case, we can find that the magnetic shear dependence is stronger in the NT case. And we are also motivated to study the isotropic features of the flow shear. But here, from this NT case, we can see a peaked strong flow shear in the core. However, for the PT case, we can see a bifurcated strong flow shear at the edge. From this peak, we can also get some indication that the bifurcation is not always accompanied by the reduction of amplitude. So as a result, its tolerance to the ballooning angle shift, it could be higher. That could facilitate the sharing of turbulence. So this could be a reason for the higher transition power threshold in NT plasma. For discussion of the flow shear in NT-plasma, it has been reported that the shaft north shift is stronger in the NT-plasma, and we find that the shaft north shift has a synergy with triangularity. Since Tokamak eddy is typically assumed to be localized near low-field side midplane, a strong peak will be favorable, but if there is bifurcations, it will impact the flow shear significantly. Also, we found this peak here. The peak strong flow shear in the core could be a reason for enhanced confinement and higher H-mode transition power threshold. So in summary, we derived an expression of the flow shearing rate in Miller's geometry. It shows the effect of shaping. And the triangularity, including its gradient, induce poloidally varying distance between flux surface elements. PT and NT impact the variation differently, so they impact the peaking of flow shear differently. With parameter from D3D L-mode plasma, we found that flow shear in NT plasma peaks. It peaks at the outboard midplane. Furthermore, the dependence of flow shear on magnetic shear is stronger in NT plasma. And finally, PT plasma and NT plasma exhibit different anisotropic features of flow shear. That could be a reason for different transport features in those plasmas. In the future, we will run gyrokinetic simulations to characterize the eddy shape and ballooning angle shift of the turbulence. That could also impact the shearing efficiency. That's all of this summary. Thank you.